So we've built a lot of the background stuff for Bohr theory already, so we're going to start with what Bohr would have known as he was building his theory. So the one thing that he knew that we've also taken a look at is that light is a form of energy. We need to be more specific though, and Bohr ends up being quite specific, that the amount of energy is dependent upon the wavelength. And if you have a shorter wavelength, you're going to have more energy. Longer wavelength, less energy. And that ends up playing into something called the electromagnetic spectrum, which runs all the way from radio waves on the very long wavelength, all the way up to X-rays and gamma rays on the very, very short wavelength. And it's all the same stuff. It's all the same form of energy. It's just different amounts of energy based on the wavelength. And you'll see that visible light is also in there in a very, very narrow band of electromagnetic radiation. That also then means that the different colors of light are going to have different amounts of energy. And that means if I know the color, I can translate that into a certain amount of energy. He also knew that every element has a unique line spectrum. And what that means is if I were to look at a light bulb, if I were to look at the sun, if I were to look at all the colors that are produced in that, look at that light through a prism, I get all the colors of the rainbow, really, really, really familiar to us: red, orange, yellow, green, blue, violet. And I guess I'm working the other way, but I know the mnemonic. If I were to look at the light produced by a hydrogen atom, though, I would not get all the colors of the rainbow. I would only get some of the colors of the rainbow. I would get very, very specific colors. And you can see here, this is what's called the hydrogen emission spectrum. And I get one line of red, not even any old red, but that specific red. One line that's sort of a greenish blue, one line of purple, and then, or bluish purple, and then one line that's a little bit more purple. Those are the lines that I get. And if I were to look at the same thing for now helium, I would have different lines. And it doesn't really matter what they are, but the point is each element has a very, very unique set of lines. Now what that means, and what that told Bohr, is that every element has a unique set of energies. Remember, light is energy, color is energy. So different colors, different energies. Different specific colors, different specific energies. And that's going to become a pretty common theme. If I then look at Bohr's theory in the statements, and these are the statements of Bohr's theory, more or less, I'm probably paraphrasing a few of them, but he said that electrons orbit the nucleus in specific energy levels. And I'm going to use the phrase specific energy levels all the time. I don't talk about shells. I don't even really talk about orbits all that often. I'm going to talk about specific energy levels because I need you to keep hearing that so that you keep thinking that. Electrons in higher orbits generally have more energy. So if you have an electron in the first energy level compared to an electron in the second energy level electron will have more energy. An electron can absorb a certain amount of energy, or a specific amount of energy, and then it's going to jump from one energy level to the next energy level. It has to absorb the right amount of energy. Not enough energy won't make the jump. Too much energy, it's not going to absorb any more than what it needs in order to make the jump. And that becomes then a question that I might ask. Well, if I give it enough energy to jump up 2 energy levels or 3 energy levels, okay, great. But if I only give it enough energy to jump up 2.5 energy levels, it will absorb what it needs to jump up 2 and no more. And if we keep going with that, once those electrons are at that higher energy level, they're not going to stay. They're going to fall back down. And when they do fall back down, that energy that they absorbed has to be released. And it's going to be released in the form of light. Because it's falling a specific amount, it's going to be giving off a specific amount of energy, which translates into a specific color of light. And that answers that question, but you might have missed it. Okay, if I look at the colors of the hydrogen spectrum and I were to look at the amounts of energy that are coming out, I can turn that into understanding what it is or which energy levels are being involved. So if I think about that, all those different colors that I was able to get for hydrogen, and any one given atom might not be doing all of those things all at the same time, but if I have a collection of those hydrogen atoms all doing that, or if that hydrogen atom goes through a bunch of turns, Then I had a red line, a greenish blue line, and a blue purple and a purple line, and those would translate into different energy transitions, which would translate into different energy levels, that an electron falling back down from a higher one to a lower one, and I could figure out the amounts of energy in the hydrogen atom, or in the specific energy levels for the hydrogen atom, based on those. Okay, and that's how it ends up working. We're not going to be doing a whole lot of that math, but we do want to kind of understand what's going on with hydrogen anyhow. Now, the numbers, not important, but the idea that different colors, different energies, which color has more energy, and then which energy transition would that relate to, yeah, that matters. Okay, electrons are going to work with the lowest energy level available to them. They're not going to be higher energy unless they have to be. But one of the problems that Bohr theory ends up with is that it cannot explain the order of fill. We're not going to get into the details of that simply because we can't. When we do get into a little bit of it, all we're going to say is, Bohr doesn't know, we don't know either. Bohr theory is going to be the one that we use, even though, if we're honest, it is not the currently accepted model of the atom. It's a pretty good model, and it's going to do pretty much everything we need it to do, but there are going to be some questions that we simply cannot answer. Okay. It's a big theory. Bohr noticed, couldn't explain it, but he noticed that there was a special stability when you had 8 electrons in the outer orbit, called the valence orbit, and then valence electrons. He gave that a name, he called it a stable octet. Here's the deal. 2 things. Number 1 is that atoms are going to try to get that stable octet. They're going to react to form compounds in an attempt to achieve a stable octet. A couple of ways they can get there. You probably know these from a previous course. We're not really going to get into it now. The other thing, the second thing, is that some atoms can't do a proper or true octet, so they kind of mimic it. And then the third thing, if you want a third thing after I said 2, is that some atoms, when they react, don't get a stable octet. So there's nothing magical about the stable octet. I've seen textbooks call it a law of octet. Definitely not a law. Not something that has to happen every single time, but there is a special stability when atoms get stable octets. So they're cool if we can get them. And then finally, I think maximum number of electrons in an energy level. Not something important for us. We're not really going to end up dealing with that. But it does go back to this order of fill business, that if Bohr was able to figure out a mathematical relationship between the energy level and how many electrons can fit in there, but it doesn't mean that it's going to fill the first, fill the second, fill the third, fill the fourth, fill the fifth in that order. It kind of gets to scramble around a little bit. So if I were to look at this table, which you don't need to know, and do the math, in the third energy level, I can fit 18 electrons, but I'm not going to put all 18 in there right away and before I move on to the fourth. Okay, and you probably have drawn Bohr diagrams before, so that you know what I'm talking about there. And if you don't, it's okay. We can't explain it, so we're not going to worry too much about it. Now, I just said Bohr diagrams without drawing them. You probably have drawn them, so I'm going to assume that you haven't, and we're going to go through start to finish how we do this. So the model of the atom, Bohr diagram shows us a picture of what Bohr thought the atom looked like, showing the electrons in their energy levels, and then also shows the nucleus. But I've seen different versions of it. The nucleus isn't going to be a huge important thing for us, right? We're all about the electrons. I'm going to work it through using the periodic table, because I think if you understand how the periodic table works for this and all kinds of other things, you're in a really awesome place, because the periodic table is a pretty powerful tool. So this is the periodic table. And what you have there is you have rows and you have columns, and all of those things are going to be kind of important to us. The row is going to tell us how many energy levels we're going to need to have in that atom. So if I'm in the first row, I've got 1 orbit, if 1 energy level. If I'm in the second row, I've got 2 energy levels or 2 orbits, and if I'm in the third row of the periodic table, that means I'm going to be drawing an atom with 3 orbits, 3 energy levels. Pretty simple, straightforward. We're not going to go much past that. For 2 reasons. Number 1, Bohr diagrams get really big really fast. Number 2 is that once I'm past element number 20, actually honestly, once I'm past element number 18, I can't really properly explain the order of fill. Once I'm past element 20, I can't even predict it. So up to element 20, I could actually explain but not predict. Sorry, up to element 18, I can explain but not and predict. 20, 19, and 20 I can predict without explaining, and after that, who knows? It's messy. Then the other thing is the columns. Okay, so the column number relates to the number of outer or valence electrons. So the column numbers are going to be at the top, and they go 1, 2, 3, 4, all the way across to 18. We're going to just deal with the ones digits. So the 1, 2, and then when we get to 13, we'll think about it as a 3, 4, 5. So things like that. So group 1, 1 valence electron, group 13, 3 valence electrons, group 17, 7 valence electrons. And that'll be kind of a quick check for us to make sure that we know what we're drawing. So a couple of examples. We're going to work with carbon, has the atomic number 6. If you haven't found it on the periodic table, go have a look. And then what I'm going to do is I'm going to count it out in terms of numbers of boxes, numbers of places on the periodic table, numbers of electrons that I'm going to be drawing. So I know it has 6 protons, and also is going to have 6 electrons. There will be times when we don't have the same numbers, but we will always start with that. If you found it, it's in row number 2. Remember, 2 rows means, or second row means 2 energy levels. And column 14. Column 14 means 4 valence electrons. Okay, so those are the kinds of things that we're going to need to know before we start drawing these things, or as we draw them, I guess. As I work my way to carbon, starting with number 1 all the way up to number 6, I'm going to go all the way across the first row. First row has 2 boxes. First orbit has 2 electrons. Then I'm going to work my way across the second row. Second row has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4 to get to carbon. 4 boxes to get to carbon, and that means 4 electrons in the second orbit. So if I were to draw them, I would end up drawing this. A nucleus. I like the full nucleus. Some people just like the symbol. First row, first orbit, 2 electrons, 2 boxes. Second orbit, for the second row, 4 places in that second row to get to carbon, 4 electrons in my second orbit. And there's my Bohr diagram for carbon. Too easy. Try one more, just so that we all know what's going on. Find sulfur. It's in element number 16. If you found it in the periodic table, it's got 16 protons, 16 electrons. It's in the third row, so 3 orbits. Column 16, so 6 valence electrons, same as before. And then building it up from the first row, second row, third row, they go all the way across the first row, all the way across the second row, almost all the way across the third row, and I would have 6 spaces across this third row in order to get to my sulfur atom. Okay, so that's what my diagram is going to look like. 2 in the first, 8 in the second, 6 in the third. Start with the nucleus, go all the way across the first row of the periodic table, which means the first orbit of the atom, 2 boxes, 2 electrons. Draw my second one because I'm going all the way across the second row of the periodic table, so that means all the way filling up that second energy level. So 8 boxes on the periodic table, 8 electrons on my atom, and then finally my third row means third orbit all the way across to get the sulfur. That means 6 spaces, 6 boxes on the periodic table, 6 electrons on the diagram. And that is it. That's Bohr diagrams. Now we'll talk a little bit later about how do you do ions, how do you do it when there's not the same number of electrons and protons, but we'll get there. Okay, you should be able to compare amounts of energy based on the colors of light. Kind of what we did before, where, okay, if this red light versus this green light, which one has more energy and which one would represent a larger energy transition if it was produced by a falling electron. You should also be able to, almost what I said. You should also be able to describe the behavior of atoms using Bohr theory. So energy in, electron jumps up, electron falls back down, energy out. That kind of thing. We'll give you some really specific examples in order to do that, where you'd have to build that out, but that's basically the thing. And then finally drawing Bohr diagrams for the first 20 elements, although I'm probably not going to do much past 18. Again, they get really big really fast, and they don't really help us to go that much larger. Okay, that's it. If you have questions, let me know. And otherwise, we'll see you when we see you.